Nothing like listening to the sound of ocean waves to learn about the nature of waves. Waves crashing onto the beach are obvious ones, but we're just scratching the surface of what waves are all about. Think about it. What are all the different waves you know? Look up. Light waves from the sun, that's another wave. Sound waves from music, voices, laughter. Waves move in a sine curve. They have a defined harmonic rhythm. So the swinging of a pendulum, the repeated up and down of a yo-yo, or jumping rope are all examples of wave motion. Waves even help us understand earthquakes. More on that later. To talk about waves, it's good to know certain key words. Through the power of video, let's freeze a wave. The crest is a wave's high point. The trough is its low point. To write a wavelength, you use the lambda symbol. This is a lambda. One wavelength is measured from the crest to crest, or trough to trough. On a graph, let's start from the point of origin and go to where it touches the x-axis the third time. That's also one wavelength. Like ocean waves, other waves don't stand still either. They move. If you measure how many wavelengths pass a certain point or count the number of crests that pass by per second, that's its frequency. A longer wave will have fewer crests, which means a lower frequency compared to a shorter wave, moving at the same speed. The period is the time it takes for a complete wave cycle to happen, from one crest to the next. So appropriately, period is written T. 1 over a wave's frequency equals its period, T. And 1 over period equals frequency, F. They're reciprocal. So here are some periods that all of us experience. What's the period for the Earth to go around the sun? About 365 days, right? And what is the period of the Earth's rotation spinning around its axis one complete time? About 24 hours. If you think about all the different waves, you can already figure out there are a lot of factors influencing the period of a wave. Here's a wave you probably never realized. Pendulums make waves too. If I move this pendulum, the period of the wave is how long it takes to go from one side to the other and back to its original position. In this case, the period is in seconds. Now, if I swing it with a little more force, the pendulum moves faster over a longer distance, so the period stays the same. With a lighter tap, it moves more slowly over a shorter distance, so again, the period stays the same. When the pendulum is at rest, it's at its equilibrium. The rhythm and motion varies depending on the length of the pendulum. Okay, if I shorten the string, what happens to the wave? The periodic motion changes. It swings more quickly, so a faster period. If I add more length, it swings more slowly, and the period is much longer. The formula for the pendulum's period is T in seconds equals 2 times pi times the square root of the fraction length, L, in meters divided by the acceleration of gravity, G, which is in meters per second square. So you can see in this equation, gravity affects the pendulum as well. Gravity is always pulling the pendulum back to its equilibrium. The force of gravity on the pendulum depends upon the pendulum's altitude, or its distance, from the center of the Earth. For example, on the Moon, gravity is much less, which means the acceleration is slower, and the period is much longer than it is on Earth. By the way, if you add weight to the pendulum, it doesn't change the period of its wave. Weight is not a factor. And some waves, like a pendulum, have a rhythmic or harmonic motion, which is a repetition of the wave with the same frequency. So think of a wave as a vibration, a disturbance that moves through space, and a wavelength shows a wave's complete cycle. Looking at a wave on a graph, the x-axis is the wave's equilibrium position, where its height is 0. A cosine wave is the same as a sine wave, except it's shifted. The peak begins higher on the y-axis instead of the midpoint, like a sine wave does. The amplitude of a wave is measured from the x-axis to the peak or crest, or from the x-axis to the trough. the distance from the resting point or equilibrium position to the maximum or minimum intensity. And again, the period is the length of time it takes for a wavelength to pass a point or to complete a cycle. And frequency is the number of those cycles that pass a point in a second. Most waves that we think about are mechanical waves, which means they need a medium in which to travel. Now, what's not a mechanical wave? Electromagnetic waves, which include radio, visible light, and X-rays. They don't need a medium. They can travel in the void of space just fine. That's why we can see light from stars and can pick up radio waves from them. Now, how fast is a wave moving? The speed of mechanical waves depends on the medium they're traveling through. Sound waves travel more than 4 times faster in water than in air. The velocity of a wave is written with the letter V and calculated by multiplying the wave's frequency, small f, times the wavelength. There are 2 ways waves can move. Can you guess? Longitudinally and transversely. Longitudinal waves are compression waves. They move in the same direction as the force that creates them. As these waves move, they stretch and compress matter or particles in their path. Here's an example. When all the coils of this slinky are equidistant from each other, this slinky is at rest. That's its equilibrium position. Now let's add a little force. I'll push one end of the slinky. Watch what happens to the coils as the wave passes through. The coils compress, which means they get closer to each other compared to when they were at rest, right? And they get farther apart here. Now, think of it like this. Where they're farthest apart, you can think that they are more rare than in other parts of the slinky. That's called rarefaction. So, as I keep adding the same force with the same rhythmic beat, the compressed coils move down the length of the slinky. Check it out. Compression. We have created a longitudinal wave. You'll see in other segments that sound waves move like this too. So, what is the amplitude of these slinky longitudinal waves? The amplitude is the distance from the equilibrium position coils at rest to the maximum or minimum intensity. The second type of wave is a transverse wave, which we can also show with a slinky. They look like sine waves. Okay, with what you know about waves, let's go underground, because with earthquakes, you get both transverse and longitudinal waves of varying magnitudes. And you've seen the devastation they can cause. These waves can pack a powerful punch. When plates in the Earth shift, they create seismic waves. They're what scientists monitor to locate the epicenter of the earthquake. Seismic waves come in 2 varieties, P and S waves. P waves, where P stands for primary, are longitudinal and move quickly through the Earth. S waves are secondary waves. They're transverse waves. They travel more slowly and can be very destructive. Springs make waves too. Pull on a spring, and you can see there's a harmonic action from rest to bouncing down and up and down and up. Each spring has a different ability to restore itself, to bounce back to its equilibrium position. That's called the spring constant. The force required to pull the spring away from its rest position is given by the equation F equals negative K times X, where F is the force, K is the spring constant, and X is the displacement from the rest position. The negative sign is there because the force opposes the motion of the spring getting back to its rest position. The potential energy of the spring at rest is 0. But the potential energy of a stretched spring is 1/2 kx squared. Here's how to figure out the energy in a spring that oscillates and has a wave-like motion. You should know the spring constant, which describes how stiff or strong the spring is. The higher the spring constant, the more force it takes to stretch or compress it. Every spring has a spring constant, and it's not always the same for every spring. Springs are different because they do not apply constant forces. The more a spring is stretched, the greater the force pulls back on you. So are you getting the gist of all this wave action? Just look around you and you'll see that waves are everywhere. Just dive right in.
For more practice problems, lab activities, and note-taking guides, check out the Physics in Motion Toolkit.